In this video, we're going to be taking a look at ray diagrams for mirrors, flat mirrors, concave mirrors, and convex mirrors to see what happens to the image produced. So let's start out with our flat mirror. If we have a person looking at a flat mirror, these diagrams are usually fairly simple, and you basically just have to use the law of reflection and then also use a couple methods with your ray diagram in order to produce the image. All right, so to produce this image, I just drew two light rays moving towards the mirror and two reflected light rays. So the way the light would actually travel, it would come down from some kind of source, like maybe a light on the ceiling, and then maybe hit the person's foot, get reflected up to the mirror, bounce off the mirror, and then towards the person's eye. And if you drew a line perpendicular to the surface, then we can see our angle of incidence, which is the angle that the light rays come in to strike the mirror. And then we have the angle of reflection, which is the angle between the light ray reflecting and the normal towards the person's eye. So the law of reflection says that in all cases, the angle of incidence equals the angle of reflection. So basically whatever angle it comes in on is whatever angle it bounces off at. So we have two reflected light rays to move to the person's eye, which is this one. And this one over here. And if you were drawing a larger diagram and being a little bit more accurate, then you would use a flat edge and a protractor to create this perpendicular line. And then you would measure this angle and then this angle to make sure you have the proper angles for each of your light rays. So I'm just drawing the quick sketch so that we can just talk about what ideas are the main ideas for drawing these ray diagrams and what they're supposed to look like and why we see the things that we see. So now we have those two reflected light rays, and our brain doesn't know if it's a light ray that's coming directly into our eye or a light ray that's reflected. So it appears as if this reflected light ray is coming from back here, and it appears as if this reflected light ray is coming from back here behind the mirror. So it appears like the top of the person's head is over here, and it appears as if their feet are from over there. And we call this a virtual image because we see something that is behind the mirror where the light isn't actually collecting behind the mirror. So that's called a virtual image because it's on the opposite side of where the light is actually coming from or bouncing around. So every time we see our full length of our body as a reflection, it looks like it's the exact same size as the actual object itself, and then also looks like the depth away from the mirror is the same as the distance we're standing from the mirror on this side. For these reasons over here of how the light is reflected and how our brain thinks that it's coming from behind the mirror, the same distance that we're standing away from the mirror. Now let's take a look at 4 different examples that we're going to be working on, and we have a few basic rules. So let's just talk about what some of these main points are before we hit some of these rules. So we have our curved mirror, and the reflected side is on the left side. So for these concave mirrors, it's on the left side of the curve on the inside, and then for our convex mirror, the reflective part is on the outside. So basically for all our pictures, it's on the left side. And we have 2 points for each of them. We have F, our focus or our focal point, and then we have our C, our center of curvature. So the focal point is the point at which if we have a bunch of light rays coming in a straight line, they would all bend through the focal point or the focus. Okay, and then our center of curvature is basically if we take this curve and complete our circle here. That would be the center of our circle, which is 2 times our focal length. All right, so when drawing our picture, our objects are usually just drawn as an arrow. So I'm going to go ahead and just draw an arrow here. So there's our object. It is standing upright and it's facing the inner curve of this concave mirror. So let's go ahead and label these as concave. And what we're going to do is we're going to mostly just use these couple rules over here. So if you just take a look at the curvature of the mirror, you can kind of get a pretty decent sense of which way the line is going to be reflected. So it still does follow this rule where the angle of incidence is the same as the angle of reflection, but it's a little bit harder to work with those ideas with the mirror that's curved. So generally speaking, I would say that if you drew a light ray straight into the mirror, it's going to reflect through the focus. And if you draw a light ray through the focus, then it's going to bounce off straight with this reflected ray. And it'll look something like this. All right, so I finished about all the different combinations you would see for a concave mirror. So if you have anything outside of the focus, you're going to get a similar image. So what I did was I took a look at this curvature here, and you can see how it sort of tries to bend everything towards the center, right? Because it's a concave mirror, it's bending everything towards the center. So our general rules of thumb is if we go straight like this, then we're going to bend through the focus. And then if we go through the focus, then it's going to reflect straight. So then if we reflect away from the center is going to try to bend it towards the middle a little bit, and then it just is going to come out straight. So it looks like the light rays are going to be intersecting at this point over here, and we are going to get an image that's considered real because it is on the side of the mirror where the light is collecting. It's going to be inverted because it's upside down. And then we're going to say the size of the image is the same. So if you were to like measure this length right here, we'll say that if it goes like a few inches up, then it's going to go a few inches down. So only if it's right on the center of curvature, its image is going to be exactly the same size. If it was a little closer or farther, it would still be real and inverted. But it's just going to end up being like a little bit smaller or larger depending on where you slide that image. Okay, for our middle case here, it looks like it's not done because there is no image. So if we were right on the focal point, we can go straight and then through the focus. So we have a light ray that goes straight into the mirror and then gets reflected through the focus. And then if you try to send one through the focus, then you don't really get any light that would hit the mirror at all. Okay, so there's absolutely no image at that point. So what would you see? You would basically see, maybe some sort of things reflected. But if you walk towards a concave mirror and then you're standing right at the focus, you would see a fairly clear upside down image as shown over here. And then once you reach that focus, it's going to look pretty blurry. Now, when you enter inside the focus, something sort of interesting happens here too. Now, if we try to draw our light ray straight and through the focus, we can go ahead and do that. It goes straight into the mirror and then reflects back through the focus. And then we have through the focus and then straight. So now we can't send a light ray backwards because it's not going to actually hit the mirror. So what you would do is take a straight edge and you would line it up right there. So you basically get your angle through the focus, but you're not actually sending the light ray backwards because it's not going to hit the mirror. So I'm going to make sure my alignment is right and then do my angled through the focus and then come out straight. So I'm going to go angled up and then straight back. Now these light rays never meet, so I'm not going to have a real image. Okay, so the rule is if you don't have light rays intersecting at all, well, this one is a special case, so we don't even have two light rays that are moving around that might intersect, so this one is a special case that's no image. But if you have two light rays that are diverging from each other, what you do is you always dot them back. Okay, so what I would do is I would take this reflected ray, and we are going to go ahead and dot that one back, and this reflected ray, and dot it back. Okay, so you only dot ones back that are reflected off of the mirror. And again, it gives this brain the perception that these light rays are coming from behind the mirror. So it's as if they meet over here on the other side of the mirror, and they produce what's called a virtual upright image that's larger. So it's virtual because there isn't actually light collecting on this side of the mirror. It's just something that the brain thinks is happening. It's upright because it's standing up, it's not upside down. And this arrow definitely appears to be larger. So if you're inside of the focal point, what happens is you see a larger upright version of yourself. All right, so moving to our very last one. Our last one is actually a fairly simple case because every image that is produced for a convex mirror comes out to be the same. And it's going to look something like this. All right, so I follow the same rules, but again, for some of these cases, there are similar rules, but the way that the light rays move around is going to be a little different. So I did my straight and through the focus. So I went straight, and it's going to reflect off the mirror. So we're not going to actually slant down through the focus because that would be on the other side of the mirror where the light isn't actually moving around. So what I'm going to do is I'm going to go straight, and then I'm going to align my straight edge through the focus to get the correct angle. Okay, and then I'm going to send my reflected light ray out, diverging away from the center. And then my second one that is through the focus and then straight. Again, the light ray isn't going to actually go on the other side of the mirror because it's reflected, but I am going to angle it towards the focus. Okay, so it's going through the focus or towards the focus, but it's not going to actually make it there. And then it gets reflected straight back. Okay, so just like we did with this drawing over here, if we have two light rays that are diverging, you always dash them back and see if your two reflected light rays intersect each other. And if they do, then we're going to have a virtual image. So we have this one. That's a reflected light ray. And we have this one. That's a reflected light ray. So we're going to have a little arrow right over here. We're going to consider that to be virtual because it's on the other side of the mirror where the light isn't collecting. It is going to be upright. And it is going to be smaller. Okay, so this is a type of mirror that's going to be a little bit more practical because this one, the concave one, can flip ones upside down, create no image, and then make some that are going to be a little bit larger. But this one's going to be more practical because it's always going to give you a virtual upright smaller image. So what they might do is place them in stores, like in the corner of stores, and it's going to make everything smaller, so it's going to give you a greater range of vision. So they might be in corners of stores, corners of parking garages, or also the mirror, the passenger side side view mirror, so that it can give you a wider range because it makes everything a little bit smaller. So the mirror that is farther away from you has to have a greater range because the angle at which you're looking at the mirror, you can't see quite as much as the mirrors that are right next to you, which is the driver's side view mirror or the rear view mirror. So those are a little bit closer, so you're going to be able to see a little bit more with those. But with the passenger side view mirror, that one is going to be actually a slightly convex. So then that way you have a wider range of vision, although it does kind of shrink everything just a little bit to get that wider range of vision. All right, so to sum things up, all these light rays follow the law of reflection, where the angle of incidence, which is the angle that it comes in at, is the same as the angle of reflection away. And when you do each of these images, like I said, they're pretty much following these rules with some slight variation. So once you get enough practice, you're going to notice that you're going to kind of get the hang of it. It's going to become easier the more practice you get. So if the light rays do actually start converging on each other, then you have a real image. And then if they don't converge on each other, then you're going to dot them back to see if you have a virtual image on the other side. So I hope that was helpful in helping you understand mirrors. With lenses, you can basically follow two rules, which are sending a light ray through the center of the lens, or sending a light ray straight to the lens and then bending it through the focus in some way. So on the top row over here, we have three converging lenses. You could either call them a converging lens, or you can call them a convex lens. And on the bottom here, we have two diverging lenses, or you can call them concave lenses. So as I said earlier, with all of your lens diagrams, you can draw a light ray through the center of the lens, or you can also draw it straight into the lens and then do some sort of version of bending it through a focus. So on our top here, we have three convex lenses, and I'm going to start off drawing a diagram with the object outside of the focus, one on the focus, and then one inside of the focus to see what type of images we produce. All right, so for all of our top diagrams, we have all of our light rays converging towards the center. So a basic rule of thumb you can use for lenses is that the light rays always bend towards the thickest part of the lens. So for all of our convex lenses or converging lenses, it pulls the light rays towards the center. So as I said, we can always shoot a light ray right through the center of the lens. That's kind of like our free light ray for our convex lenses and also our concave lenses. So that's kind of your free one. You can use that on each one of them. And then for all the rest of them, you send one straight and then through the focus. So I sent one straight and then converge it down through the focus. And we have an image that is real, inverted, and for this one in particular, the size is going to be exactly the same, which is usually not the case, but this one is exactly double the focal point, so it ends up being exactly the same size as the actual object itself. Okay, it's considered a real image because it's on the other side of the lens. So as opposed to mirrors, mirrors have real images that are on the same side of the object because the light reflects back onto the same side of the object, as opposed to lenses where they're transparent and then the light actually goes through them. So this is the real side, and then this would be the virtual side. This is considered inverted because it's obviously upside down, and then based on the size of the image compared to the object, you would call it smaller, the same, or larger. In our second case, it's a very unique case where the object is directly on the focal point. So if we send our light ray through the middle and then the other one straight and bend it through the focus, what happens is these light rays are parallel, so there are no images produced. For the final one, we have our image inside of the focal point. And what happens here is we send one through the center of the lens as we did with the other ones, and another one straight and through the focus. And then if you can tell, they're not exactly parallel. This one is kind of diverging away from this line a little bit. So what you do with this scenario is similar to what you do with any type of lens diagram. If you have two light rays that are not converging on each other, then what you do is you always dot them back to see if you have a virtual image. So if I go ahead and dot this one back, and dot this one back, we do have an intersection back here. And this image would be considered virtual. Because as I said before, the light that would reflect the object goes through the lens. So this is the real side, and then this is the virtual side. Our image is upright, and it is clearly larger. Okay, so this is basically how a magnifying glass works. If you have something within the focal length of the lens, then it's going to enlarge it, and if you look at something far away, it's going to look inverted. All right, now for our final diagrams, we're going to do a concave lens diagram. Now, all of these are pretty much the same. I'm going to draw two so you can see how similar or different they are. But for most of the concave lens diagrams, they're going to be pretty similar. All right, so if you take a look at both of the concave lens diagrams, they look fairly similar, as in they have one light ray going right through the center, just as we did with our other ones, and then we have one that goes straight. And then this version of straight through the focus is a little bit different. Remember, it's a diverging lens, and also, as I said earlier, a lens always makes light rays bend towards the thickest portion of the lens. The thickest portions are always the outer portions for a concave lens. So they're basically bending away from the center, the exact opposite of a convex lens. So what I did was I drew a light ray right through the center for both of them. And then for the second one, I did the same thing. Instead of sending it straight through the focus, I did straight and aligned it with the focus so I could see which angle to diverge it on. So same thing with this one over here. I aligned it with the focus. Okay, now because these two are diverging from each other, just like we did over here, we always dot it back to see if we have a virtual image. And I did actually already dot this one back. And if you dot this one back, you're basically tracing the same line. So for both of them, you get a similar image. Okay, both of them are virtual because they're on the same side as the object. They are upright, and they are definitely smaller. All right, so to sum up everything we did for these ray diagrams, for all 5 of these different diagrams, the easiest one to remember is the light ray that you shoot right through the center of the lens. And then for our converging or convex lenses, we sent the light ray straight into the lens and bent it through the focus for all 3 of them. And based on what happens as a result, you may have to take some steps after that. This one we had our intersecting point, so we already knew where our image was. Right on the focus is our special scenario that has no image. And then the very last one over here inside the focus follows our rule. If the 2 lines do not intersect, you dot them back to see if there's a virtual image produced. Okay, for our second ones, we shot that light right through the center, and we did a version of straight and through the focus, but we just aligned it with the focus so we knew how to diverge that line. And these 2 clearly do not intersect. So what we did is we dotted them back, and we had a virtual, upright, and smaller image for both of them. I hope that was helpful in helping you understand ray diagrams for lenses. Thank you for watching and listening.